Hi, my name is David Villar. I teach pharmacology at a veterinary school in the country of Colombia. Welcome to this other video that will review one of the steps of pharmacokinetics, which is the elimination of drugs from the body. So what do we mean by elimination of drugs from the body? Well, as the name implies, the body is always acting to eliminate foreign substances when they enter. So if we were to give this dog a pill containing a drug, it will do whatever action it's supposed to do as long as it's present at therapeutic levels. But there are going to be organs like the liver and the kidney that will remove or eliminate that drug. And as you can imagine, from a practical standpoint, that's going to result in the termination of the action. So if we know how fast the drug is eliminated and at what concentrations it's required to attain a therapeutic action, we can estimate how much and how frequent we need to keep administering this drug. So what are the two physiological processes that are involved in elimination? Well, the first one is metabolism or biotransformation, and the second one is excretion. In the metabolism one, there are going to be enzymes that are going to convert the parent molecule into a different one. And in this cartoon, basically the parent molecule is being broken up into two different smaller ones. And if we look at this other diagram, there are going to be many drugs, especially very lipophilic ones, that will have to be metabolically converted by enzymes like the cytochrome P450s, which basically convert drugs into more water-soluble oxidized molecules, which are going to be easier to be excreted, or they can be further bound to molecules like glucuronic acid, and that will definitely make these drugs a lot easier to be excreted out of the body. As I mentioned earlier, most of these enzymes will be in the liver, but there are also going to be other organs that can carry out these metabolic processes. And it's not shown here, but many drug interactions take place because they either inhibit or induce some of these metabolizing enzymes. Now, with regards to the excretion, the most common route is going to be through the kidneys and out of the body with the urine. And obviously, the drug needs to be reasonably water soluble to remain in the fluid that is going to become the urine. And as you can imagine, patients with impaired kidney function will usually have a reduced ability to eliminate at least the hydrophilic drugs. And in order to avoid excessively high concentrations in these patients, we usually either have to reduce the dosage or give them less frequently. There are going to be a few drugs that obviously enter the bile duct and that are going to be excreted with the feces. And if you notice in this diagram, sometimes metabolism results in drugs being converted to a more reactive metabolite, and sometimes these metabolites can be toxic. Now, how is the elimination calculated and viewed graphically? Well, most drugs are going to be eliminated through what we call a first order kinetics. So if we were to collect blood samples at different times following the administration of a drug, in this graph by an intravenous injection, and we were to measure the concentrations in plasma, we would typically see a curve that declines over time. So because it's usually very difficult to make calculations unless we have a straight line, in order to determine pharmacokinetic parameters like the half-life, what is usually done is to plot the concentrations in a semi-logarithmic scale. And as you can see here, when the y-axis is changed into a log scale, that curve now turns into two straight lines, which correspond to two different phases that can be easily distinguished. In that initial phase, what's happening is that the plasma concentrations are steeply declining, and the second linear phase, which you notice here, is less steep. So basically, what's taking place is that right after the injection, the drug will be mainly present in the blood compartment, but it's going to rapidly distribute into tissues. And since the interstitial space is usually 4 times bigger than the plasma compartment, that initial steep phase is called the distribution phase, because the drug is basically leaving the blood compartment and going into tissues. So this early rapid decline usually takes place within minutes, and basically the body is acting kinetically as a single compartment. Now, once the drug has distributed into the tissues and the concentrations reach an equilibrium with those in plasma, then the second slower decline of the plasma concentrations take place, and this is associated exclusively with the elimination of the drug from the body. In other words, this second phase is going to correspond to the kinetics of elimination, and therefore this phase is called the elimination phase. And the two parameters that are going to be associated with this process are the constant of elimination and the elimination half-life, and these two can be estimated from the terminal slope of the concentration time line that you see here. Now, the other pharmacokinetic parameter that can also be calculated from this graph, and which is important in calculating dosages, is the volume of distribution. So if we know the dose given to the animal, we can divide it by the concentration that results from extrapolating the terminal slope to time zero, and that will give us the volume of distribution of this drug. And really, with the volume of distribution and the constant of elimination, we can pretty much calculate the maintenance dose, and that's explained in more detail in another video. So as a final slide, let's show an example of elimination causing differences between dosing dogs and cats. And I use aspirin as an example. Aspirin is acetyl salicylic acid, and the major elimination pathway involves binding to glucuronic acid to form an ester conjugate, which is more soluble and can be easily excreted with the kidneys. And unfortunately, cats lack this glucuronidase enzyme, and therefore they're going to take longer to eliminate aspirin. And this basically explains why the typical dosage of 10 milligrams per kilogram, which is given every 8 to 12 hours in dogs. In cats, this should be spaced to every other day, basically. And it also explains why many non-steroidal anti-inflammatory drugs like aspirin are more toxic in cats and consequently are contraindicated in this species. So this is the final slide for this presentation. I do encourage you to take a look at the one that we prepared explaining where maintenance and loading doses come from. And as you will see, these pharmacokinetic parameters of volume of distribution and half-life of elimination are the parameters that will be used to calculate the dosages that you will typically find in most drug formularies. So I hope this information was helpful, and until next time, I say bye-bye for now.